Hello, algorithm enthusiasts. Today, let's understand QuickSort through a real-world example. Imagine you're organizing books on a shelf by height. You might naturally pick one book as a reference and arrange others around it. That's essentially QuickSort. QuickSort is a recursive algorithm, meaning it breaks down the big problem into smaller, manageable chunks. Instead of sorting everything at once, it divides the array into smaller subarrays and sorts them independently. Let's see how this works with our example array. Here's our unsorted array. First, we'll select 25 as our pivot element. Think of it as our reference point for sorting. We remove the pivot and set it aside, leaving a gap in our array. Now we'll use two pointers. One starting from the left looking for number larger than 25 and one from the right looking for numbers smaller than 25 to organize elements around our pivot. From the left, we find 64, which is larger than 25. From the right, we find 11, which is smaller than 25. We swap these elements. Now, 11 is correctly positioned before our pivot and 64 after it. Moving our pointers inward, we find 35 from the left and 22 from the right. Again, 35 is larger than our pivot 25 and 22 is smaller, so we swap them. The pointers cross each other in their fourth iteration. The fourth place is where our pivot belongs. When we place 25 here, we guarantee all elements to its left are smaller and all elements to its right are larger. Now we have two smaller subarrays. QuickSort recursively applies the same process to these subarrays until everything is sorted. The right subarray, 35, 64. 90 takes just one quick check to confirm it's already sorted. The left subarray needs one small sort, and voila, we have our fully sorted array. Let's talk performance. On average, QuickSort runs in O(n) times log n time, making it one of the fastest sorting algorithms. Space complexity is O log n for the recursive calls. However, in the worst case, time complexity can be O(n) square, though this is rare with good pivot selection. Want to see this in action? Check out our interactive visualization app in the description below, along with a Python implementation you can try yourself. Hit subscribe for a new algorithm explanation every day. Until next time, keep coding.